In the last video, we took a look at some special considerations for objects moving in circular trajectories in a vertical plane. And we also took a look at orbital considerations as well. We're going to take a bit more of a dive into planetary orbits here. But to do that, we have to present Newton's model of gravity known as his law of universal gravitation. So in the model of gravity that Newton came up with, which he worked out by very careful analysis of the shape and period of orbits. He deduced that if we have two objects, say mass m1, mass m2, we already know by Newton's third law of motion that the gravitational force, the gravitational attraction between them has to be equal and opposite. So the form of the third law has to be such that it reflects this equal and opposite nature. And it turns out that the magnitude of the force, the direction is always attractive. The magnitude of the force is equal to big G, so don't confuse this with little g. Big G m1 m2 over r squared. Now this big G is a number basically to make the units work. It's called the universal gravitational constant. It's equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So we can see that this respects the third law because of its force on 1 on 2 or 2 on 1. Both masses show up. And r is the center on center distance between the objects. So if they're point masses, it's just the distance between the point masses. If they're extended objects, it's the distance between the centers of mass of each of the objects. The proof that you can do that is beyond the scope of this course, but the math does indeed work out. Okay, so near the surface, so if we go, so how does this relate to the mg that we've seen before? So let's say we're near the surface of the Earth. So let's just think about me standing, let's just think about me standing on the surface of the Earth. Obviously this isn't even remotely to scale since I'm way bigger in this drawing than I would be in reality. So if we're near the surface of the Earth, I'm just going to mark off the radius of the Earth is RE. Now, the gravitational force on me, if we follow this through, the two objects involved are me, so we'll say my mass is little m, and we'll say the mass of the Earth is big M sub e for mass of the Earth. Plugging in, we would get G, mass of the Earth, mass of me, over. Now what distance do we use here? Officially we need to go with center on center distances, but hey, the center of me is about 1 whole meter above the surface of the Earth. And when you compare that to the radius of the Earth, that is a very small difference. So near the surface of the Earth, you can very accurately just say that to any precision you care, that the distance between the center of me and the center of the Earth is basically the radius of the Earth. And this difference is even less of a deal because of the fact that it's squared. All right, but the big deal here is we can see F, and hey, there's a little m here. So where we can link this together is to say the rest of this we identify as our gravitational field strength, little g. And if you crunch the numbers through, in the case of the Earth, you would get 9.8 newtons per kilogram. And the thing I circled here is always going to be the gravitational field strength anywhere. So if you're at the altitude of the International Space Station, that is far enough away from the center of the Earth that matters, you'd replace the radius of the Earth with the radius of the International Space Station's orbit. You do that, you'll get a little smaller number. Okay. So just to maybe make this a little bit more concrete, let's go and take a look at the gravitational field strength on the surface of the moon. So here's the moon. So again, it's the same kind of logic here, but now we're just saying this is the moon. So the radius here would be the radius of the moon. The mass we need would be the mass of the moon. And again, you're just going to stick some test object, maybe a rock or something that's just sitting on the surface of the moon. So we can play the same game. We can say that the force of gravity on our rock is basically going to be g times the mass of the moon times the mass of our rock over the radius of the moon squared. We can set that equal to mg. So g on the moon, let's say g sub moon here, will be equal to g mass of moon over radius of the moon squared. Okay, I've looked up those numbers. So big G will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass of the moon is 5.55 times 10 to the 26 kilograms. And the radius of, oops, I'm sorry, that's not the mass of the moon. That will be the mass of Saturn later. The mass of the moon is a much more reasonable 7.36 times 10 to the 22 kilograms. And the radius of the moon is 1,737.4 kilometers, or 737,400 meters squared. Crunch that all through, you will get 1.622 newtons per kilogram, about a sixth of what G on the surface of the Earth is. And you can really see the effects of this. If you go and look up videos of the astronauts walking on the moon, you'll notice first off that they don't even really walk. This is because the act of walking is a controlled fall. You push off with your back foot and swing over your front foot and then fall down and catch yourself with the back foot now having been swung over to be the new front foot. The length of our limbs and everything is pretty much built around G being 9.8 newtons per kilogram, not 1.6. So this is a problem. When astronauts would attempt to walk on the moon, what would happen is that they would basically just swing their leg out, and you can find lots of video of them literally falling on their butts. And this is actually kind of a big deal. You know, last thing you want to do is harm any of the life support equipment. So falling was something that you very much wanted to avoid. The astronauts very quickly figured out that it was much more efficient to basically do a bunny hop / gallop kind of motion. So if you watch, you'll see them more just like hopping from place to place. Still, doing that in a pressurized spacesuit involved a lot of exertion. And so if you're going to go any distance away at all from the base, that's why you needed to build those cute little lunar rovers. By being able to drive around, it took away the need for human locomotion, which turned out to be insanely difficult in the much weaker gravity of the moon compared to what our bodies expect. Okay. So I mentioned that Newton worked out this form of gravity by looking at orbital data. And one of the things that he looked at was an empirical observation about the motion of planets made by Johannes Kepler. It's usually known as Kepler's third. Oops. Or his harmonic. Law. And this is really an empirical observation. What Kepler observed was that if you square the period of the orbit, that was proportional to the cube of the orbital radius. So if you plot the square of period on one axis and the cube of radius on the other for all the planets, you'll find that falls in a straight line. So that was really cool. His other two laws, just by way of reminder, his first law was observing that planets moved in ellipses with the sun at one center and at one focus and the other focus vacant. This is no small feat. The orbit of most planets just barely deviates off of a circle. It's really only noticeable with Mercury and kind of with Mars. Pluto's not a planet, but you would definitely notice it with Pluto. But the other planets, the orbits are just barely not circular. So it was quite a big deal for Kepler to figure that out. And then Kepler's second law of motion was the equal areas and equal times thing. Newton took all of those and rolled it together to deduce what the mathematical form of gravity had to look like. And the reason it gets called Newton's law of universal gravitation is that he was also able to show that it turns into the mg form that we've been using near the surface of the Earth. Thus, the law of gravity is the same both on Earth and in the heavens, thus the universal part, which at the time philosophical thought was that the Earth and the heavens obeyed different laws. So it was a big breakthrough. All right, so rather than go in the direction of taking Kepler's observations and then figuring out the form of gravity, because that's way beyond the scope of this class, we can at least show that you can get Kepler's third law from Newton's law of universal gravitation and the second law of motion. So let's go take a look at a planet orbiting the sun. All right, there's the sun. Way out here is going to be some little speck. That's going to be our planet. And like I said, the orbits technically aren't circles. They're technically ellipses, but the difference isn't very large. So we're going to basically approximate this as a circular orbit. You can get the exact same result if you assume an elliptical orbit, but it is much more complicated to show. And since most of the planets basically orbit in circles, they're just barely not, it's not really worth discussing. All right. So we can go ahead. I'm just going to draw the free body diagram for the planet right on the planet here. Boom. Force of gravity. That's it. So we can go ahead and express Newton's second law of motion here. We can say that the force of gravity would have to be equal to ma. So now we'll put in the force of gravity in its full scary form. We'll say G, I'll use big M for the mass of the sun and little m for the mass of the planet. Compared to the sun, all the planets are basically rounding errors. Jupiter, you kind of notice a little bit, that's about it. Over r squared. And our acceleration, remember, is going to be v squared over r. Okay. So the first thing we notice is that the mass of the planets cancel. And we can lose 1 power of radius, but don't worry, we'll get 2 back real quick. So the other thing to think about is how can we express the speed in terms of the period, since what Kepler worked out had to do with the period. Well, the speed is going to be, we can express the speed as the distance it takes to do 1 lap over the orbital period. So we can observe that the speed will be the circumference, 2 pi r, over the orbital period. So we can put that in. So we've got gm over r equals, okay, squaring v here, square the 2, that's a 4. Square the pi, that's pi squared. Square the r, that's r squared. Square the t, that's t squared. Okay, and then we can go ahead and rearrange this to get t squared on the left and everything else on the right. So I'll multiply through by t squared, and I'll multiply through by r over gm on the other side. And there you go. So what we get is that the orbital period is indeed, the square of the orbital period is indeed proportional to the cube of the orbital radius. And the proportionality constant goes inversely as the thing you're orbiting. Now this is more powerful than Kepler's observation. Kepler's observation was only looking at planets going around the sun. Newton was able to extend that out and say, look, this is now looking at gravity and the laws of motion. I recovered Kepler's result, but we can do a more general form of this. If, say, there's a moon orbiting a planet, we can weigh the planet by looking at the period and the radius of the moon's orbit. Now, I did sweep a technical detail under the rug. This is only strictly correct in the limit of the thing being orbited being much more massive than the thing doing the orbiting. And this is usually true. However, there are a couple of notorious cases where this doesn't work out and you have to be more careful. One is, for instance, looking at Pluto, its main moon, Charon, is a pretty substantial fraction of the mass of Pluto. And the Earth's moon is a few % of the mass of the Earth, and that's just enough to mess everything up. In that case, a more detailed analysis shows that instead of this being the mass of the thing being orbited, it's actually the combined mass of the two things. Now, for virtually anything else, like say you look at Europa going around Jupiter or something like that, the mass of Europa is so much less than the mass of Jupiter that this comes down to being difference of, like, say, weighing a dog with or without its fleas. But in the case of Pluto Charon or Earth Moon, what you get is a combined mass, and then you have to, then you'll notice that the two objects actually orbit around their common center of mass, and that the location of the center of mass is where you would stick a fulcrum if you had a teeter-totter, and then you can divvy up the percentages by thinking about how a teeter-totter would balance, which we'll get to later in this series. All right, but let's go ahead and do this to, say, figure out what the mass of Saturn is. If we go and take a look at Saturn, one of its more prominent moons, so there's Saturn. One of its more prominent moons is a moon called, well, Titan's in the equatorial plane, so there we go. One of its more prominent moons is a moon called Titan. This is pretty visible with even a very modest telescope. Astronomers have very meticulously figured out the orbital radius of Titan and worked it out to be 1,211,850 kilometers. And they have very carefully measured the orbital period of Titan and worked it out to be 15.945 days. All right, so we can start, if we want, with using Kepler's third law. Nothing wrong with that. T squared equals 4 pi squared over g m r cubed. Now here what we want to find is the mass of Saturn. So we'll multiply by m, divide by t squared, get that the mass of Saturn will be 4 pi squared r cubed over gt squared. As a fun aside, before we actually crunch the numbers, I don't know if you noticed this, but there is sort of a standard way that these things get written. The usual order is you write numbers, you write digits, named numbers, physical constants, variables, and there's parameters, and then variables. So the 4 is a number, pi is a named number, so it always comes after the 4. And then R and T are both going to be parameters in this case because you're not changing them. T, they both be variables because they would change between experiments, like if you looked at a different moon or something like that. Parameters are things that don't change between runs, and things like this are and variables are things that do. G is a physical constant, so if it were up here, it would have been 4 pi squared g. So anyway, just a fun aside that there is sort of a standard order to these things. All right, anyway, let's go ahead and substitute in the values and see just how massive Saturn is. So 4 pi squared. All right, first off, you got to be very careful. You don't want to just stick the numbers in. You do have to put in the numbers with the units. And it's important to remember the units of big G are going to be Newton meters squared per kilogram squared. So these kilometers are going to have to go to meters. And also when we put in the period, because newtons have seconds buried in them, the time is going to have to go to seconds. So all right. So if I have 1,211,850 kilometers, I can make that go to meters by adding 3 zeros to it. Yeah, that's going to be a big honking number going into your calculator. And then we can put in big G. That is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And then finally, we've got to get our 15.945 day orbital period into seconds. So just remember, one day has 24 hours. Cancel, cancel. And because I run out of space, I'll jump straight to 3,600 seconds in an hour. Cancel, cancel. And that all needs to be squared. All right. So when you run that all through, you are going to get 5.55 times 10 to the 26. And we really, really hope it's kilograms, but it's probably worth checking, huh? So we are going to have meters cubed upstairs. Dividing through by Newton meters squared per kilogram squared. All right, and then this here, the days, hours, we are left with seconds. We have seconds squared there. So we can lose 2 powers of meters there. Now for the rest of this, we're going to have to expand out the Newton. So I've got a meter over. A Newton is a kilogram meter per second squared. Times seconds squared divided by kilograms squared. So cancel, 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 cancel. We are left with 1 over kilograms is kilograms. So thank God. So the units do check, and we have 5.55 times 10 to the 26 kilograms. Now, if you do it with even more fussily obtained values than what I used here, the current accepted value is more like 5.68 times 10 to the 26 kilograms. Picking up a few more digits in some of these things when you're squaring and cubing can really make a difference. So it might be kind of hard to ask yourself, if this is reasonable. I mean, after all, they call them astronomical numbers for a reason. They are really big. And about the only thing I can have to even remotely offer a bit of help, and even that's going to be a bit tough, is you can remember that the mass of the Earth, just for a bit of comparison, it turns out to be just a shade under 6,000 yottagrams. And I'm sure we're all right on top of that yotta prefix, which yotta means 10 to the 24th. So this would be 10 to the 24th grams, which would be 10 to the 21st kilograms. And so we look at this over here. This is working out to 5. If we use, say, the 5.68 times 10 to the 28, this would be like 56,800 yottagrams. So it's like, all right, it's a little bigger than, about 9, right around about 9-ish Earth masses. So I could totally believe that would be a legitimate number for the mass of Saturn. It's not a horribly memorable thing, but it's something if you're looking for a number to hang your hat on. Planetary masses tend to be 3 to 6 digits of yottagrams. All right. Well, anyway, on that awesome thought, in the next collection of videos, we will start to look at changing the rate at which things are moving around, the rate at which things are rotating. So catch you on the flip side.